Okay. Firstly, I would like to introduce a bit about the whole picture of our MindSpore. MindSpore started from March 2020, and on the same year, September, we have our first version, MindSpore 1.0, for commercial use. Current version of MindSpore is MindSpore version 1.8, and by the end of this year, or maybe the early of next year, we will launch our MindSpore 2.0. Our MindSpore is designed for the developer. It could develop once and the deployment on all the device, edge, and cloud. And we focus our study on large-scale model training, and also we have developed our application for science to accelerate AI for science. Here is our full picture of our AI software stack. Let's have a quick look at this. On the very above, we have all multi-domain expansions, such as reinforcement learning and deep probabilistic programming. Yes, we also have probabilistic programming, but today I want to talk about this part. We will focus on this part. This part is the MindCompiler. MindCompiler is our full stack collaborative optimization compiler for AI framework. And below is our runtime, and also we can deployment our model to different hardwares. So in case for the audience not very familiar with AI software stack, I will talk about a bit our graph compiler. So in the AI software stack, the graph compiler optimizes the forward and backward of the computation graph. And this computation graph is used to describe deep learning models. And MindCompiler is the graph compiler of MindSpore to achieve three major kinds of optimizations. The first part is hardware independent optimizations, such as type inference, automatic differentiations, expression simplifications. It's quite standard compiler optimization. And we also have hardware related optimizations, such as like auto parallelization and memory optimization, also graph kernel fusion on GPU, maybe later on CPU and ASIC. Besides these two kinds of optimizations and maybe standard compiler optimizations, we have deployment inference related optimizations. So this is a very specific optimization for AI models, because this is used for the inference task of AI model. So this kind of optimizations include quantization and priming. And our MindCompiler is based on a unified device and cloud MindIR. So in this way, so on the cloud side or on the device side, we share the same IR of MindSpore. Okay, so let's talk about a bit of motivation of our IR before I introduce the detail of MindIR. So what we need for IR for the compiler for AI compiler or AI software framework, compared to other general purpose IR such as LLVM IR. So we face some different challenges or requirements for the IR for graph compiler of AI framework. So here I summarize like 4 kinds of challenges. The first one is tensor representations. So as we know, for AI framework or AI model, the data it will deal with well usually in the form of tensor. So this IR should have a very nice abstraction of tensor instead of like just scalar or array as the usual language or usual compiler. And the second challenge is automatic differentiation. So yes, in today's talk, there's also other speakers talk about automatic differentiation. And so I think for a general language such as C or C++, if we have the feature of automatic differentiation, so it is a plus. Okay, so it's very nice to have such features. But for the AI framework, it is a must, because for the developer, so we can't rely on the developer to write some backward graph. So namely the derivative of the forward computation graph. So we need to have the backward graph or the derivative of the forward graph by the compiler or AI framework. The most challenge for AutoDiff is to have the universal solution for all scenarios, especially for data flow and control flow. And also, we care about the efficiency of the backward graph, because if anyone like know the situation of AutoDiff, so the backward graph is usually much more complex than the forward graph. And also, we need the possibility to extend our AutoDiff algorithm to the higher order derivatives. And the third challenge is just in time. So for AI framework, just in time is a very important execution mode. In this kind of mode, the kernel or the operator will compile while the graph is running. So in this way, so we face a very different situation of optimization of computation graph, and we need to take this into consideration while we choose our IR. And the last one, but not the least one, is implement parallelism, because it's unlike the usual HPC task. So if we write some HPC code, such as C++ of Fortune, so we can ask user to write some hint, such as pragma, to help the compiler to do the parallelization. But for the AI part, the front end is usually some dynamic language such as Python, so we can't rely on the user to write this kind of thing. So the compiler needs to analyze the computation graph and trying to find the opportunity of parallelism. Okay, so because we face these kind of challenges, so we also have a study of all the previous works and trying to find some hint from previous work. So here I list 3 of previous work, which give us some like motivation or hint while we design our IR. The first one is called Sea of Nodes. So Sea of Nodes, this is a kind of IR, and the future of this IR is like it represents the data flow and control flow as a graph, and the graph is constructed from the use-defined chain. Okay, so this kind of graph, this is very special because this is a single-tiered structure instead of 2-tiered structure such as LVMIR. It have 2 level, basic block as upper level, and instruction in the as a second level, maybe not a lower level, but this is inside the basic block. So in this way, so we have our control flow and data dependency all in the same form. So this is in the control flow and the data dependency both is implemented by the graph. So we can read the control flow and the data dependency from the graph. Okay, so this is very important. So we will mention it later how this kind of thing will work in our IR. And the second one is Turing. Turing is a functional graph-based IR. The most important feature is like it abandons the scope nesting, and the scope is some like functional. So it's like what we write. We have the namespace, we have the scope, but for this kind of IR, so user don't need to write the implement the real scope. It can be the relationship between the free variable and the subgraph is obtained from the data dependency of the graph. So this is like user will write code and our compiler will get scope directly and based on the dependency graph. And the third one, it is not like the one IR, but it's like a class of IR called a normal form. So the most important feature of a normal form is like it partitions expressions into two forms. One is atomic expression, another one is complex expression. And all complex expression must be light bind or else appear in the tail position. So here is a very simple BNF about the a normal form. So we look into these three kind of IR, and so we get motivate from this IR and observe some ideas from this IR and design our MindIR. So if you like me to use one sentence to describe MindIR, so I would like to say MindIR is a function style IR based on graph representation. So why we need to choose our MindIR to in this kind of form? This is because we choose the function IR to make our autodiff and our parallelism analysis very convenient. Because this is a functional IR. The function is the first citizen. So our control flow will represent as a higher order function. So this is a very autodiff friendly. So I will introduce later why the autodiff friendly. So because we will have the universal way to do the autodiff. So for both control flow and data flow. Secondly, if we have the pure functional IR without set effect, it is very easy to get a partial order analysis for the data dependency. And we can very easily to find the opportunity of parallelism from the computation graph. So that's why we choose our IR to be a function style. And we choose our IR is graph-based. It's like to look at like a graph, because we want the single tiered structure, and this single tier structure is very suitable for just-in-time optimization. And also we trying to design our IR very similar to a normal form, because we want to get rid of scope, so user don't need to write scope. And as we can see, a normal form IR is very easy to read and check. So we also want our IR is very easy to understand. And here is the BNF of our IR. So this is a variant of a normal form, but there is maybe I can introduce one change here, because we don't compare to the usual a normal form. We have the if statement here, but in our case we will treat our if as a primitive operation. And just like ANFIR, our IR is partitioned into like A node and C node. And A node in MindIR correspond to atomic expression of AN or ANF. And so for A node, we have two kinds of A node. The first kind is value node. It refers to the constant node. So by constant, we go beyond the constant value, such as scalar or tensor, or maybe more general is like type or shape. But we go beyond this kind of constant value because we are functional. So we treat function, and maybe this is some primitive function such as add or some NN operations such as convolution, or if the user write a function. So we also treat function as constant value. Also, okay, so this is very different compared to the usual NF. And we also have the parameter node. Parameter node, so by the name, it refers to the parameter in the function. And the main difference between value node and the parameter node is like in AutoDiff, we will consider the derivative of parameter node, but we will treat the gradient of value node to be 0. Okay, C node in MindIR correspond to compound expression in AF, indicating a function call. So I will explain very soon what does this mean. To explain this, let's look at a very simple example. So in this example, we have the function, and we have the test f to call this function, and and we can find in this in MindIR. So we represent each function as a graph. So here we have two functions, and thus we have two graphs. So here is test f, here is the function of func. So if we consider the ANF representation of this type of node, we can find our every expression is light bound. So for example, if we have a equals x minus 1, so we have a let statement is like let a equals x minus 1. So this is light bound. And in our case, we will have our expression to be bounded as a node. So let's look at here. Again, for this, a equals x minus 1. Instead of let, we have a node here. We have a C node here. C node is just a compound node, just I introduced before. And we find that the first input of this node is a sub, is a primitive function. And we have the two inputs of x and 1 here. So this C node represents, we apply this sub operation to x and 1. So this is something like apply, but we write this one as a C node. And we can find if we compute a equals x minus 1, so the next expression b equals a plus y need is a, and then we will represent this this data dependency by the edge of the graph, like this. If we need a here, and we have a collection of this a node and this C node for b, and also we have this function call, we have another edge here. Okay, so this is a very simple example. Let's look at some more interesting example of high order functions. High order functions is like we use function as like we use a function as a variable or an input of another function. So so we know in the functional programming, the function definition itself is a value. So in our case, we have 3 graphs here. It's like f is here as a graph, f is a function as a graph, g is a function again as a graph, and we have outside is HOF as a very large function, like contains g and f, and we find g take f as an input. So maybe in some other compiler, it will need some like pointer or function pointer to deal with this, but in the function But in the functional programming, it is very easy to achieve this because function itself is a value. So for the graph itself is a value. And if we look at this statement, it's like result equals, like G takes F and X as inputs. And this corresponds to this node. And this node, we take G as the first input. It's like apply G to some inputs. And the input is applies includes F as a function here. So this is the high order function semantic for MindIR. And we will see this high order semantics greatly improve the flexibility and the simplicity of the MindSpore representation. Okay, so in the function style IR, one topic we can't escape is free variable and closure. So to have a quick remind, closure is in a programming language feature that refers to combination of code blocks and scope environment. And a free variable refers to a variable in the scope environment referenced in a code block instead of the local variable. And in the MindIR, a code block is represented as a function graph. Okay, so we meet this notation a lot of times, but if we can have a quick understanding, it's like everything is like a piece of code can be treated as a graph. Okay. So no matter it's a code block or it's a function, because function is also a special kind of piece of code. Okay. And for the in the MindIR, the scope environment can be considered as the context where the function is called. So in this example, we have, if we look at the code here, we have the func_inner here, and it takes A and B from the environment. It's like the scope of function outer, the function outer here, and to take these two values to do the computation. And on the graph, we can see here. So our function inner, for sure, it is a graph or subgraph. And we find the function inner is applied here inside the function outer. And this function outer, it includes not only function inner, but also two variables or two parameters, A and B, A and B. So because function inner is applied here, then we know the value of A and B is obtained from this context. So that's why we have two lines here from the variable A here to the input here, and the variable B here to input here. Then we can by nature get the scope and get the scope of the function inner, and to obtain the value from the scope without to write the scope of A and B. So this is what we talked about. We abandoned the equivalent scope writing. So like user don't need to write what a scope for A and B. Okay. The one thing I need to mention that the capture method of free variable. So I forgot to mention that A and B here are free variables with respect to this function inner, and the function inner capture these two values by the value copy instead of reference. So I think this is mostly for the consideration is like we want to eliminate set effect, as much set effect as possible, because if we have the reference or the like pointer, it might introduce the set effect for the function call. Okay, so here is again a very interesting topic about control.
Interruption. This one, we are running slightly out of time now, and there will be 5 minutes left on your talk.
Okay, sure. So So I'm about to so I will quickly cover the rest of the materials. Okay, so here is a control flow. Control flow. So again, so control flow, we will represent our piece work, a piece of code as blocks, and we find for the control flow for if statement here. So we will have z equals a plus x plus y as the true block, and z equals y times y as the false block. But this is not like the LVMIR. We have also true block and false block, but here we have these two blocks as function, and for the switch statement, we'll choose which function to call, and in this way, we don't have the find node as in the LVMIR. Instead, it's more like higher order function selection and calling. And so in this way, we have control flow and data flow in the same form. And this is very easy for the AutoDiff implement in MindIR. Okay, due to the time constraint, so I won't talk too many details about AutoDiff, but what I need to talk is like MindIR implement the AutoDiff based on a source transformation. Is like the source for the forward function will transform to the source of the backward function, and the previously features of MindIR make this auto differential algorithm very robust because it can not only work on data flow, but it can work on the control flow in the same way of data flow because all the control flow is in the form of the function call. Okay, so I won't go to too many details here. So what we can see is like because this is a source to source transformation, we will transform the forward IR and to the backward IR here. Okay, lastly, I would cover a bit about this because this is not for the design of IR, but this is a feature for MindSpore. I like it very much because MindIR is not only an IR for compiler, we can also export it and as a model. If we train the model or we obtain some model from the MindSpore hub, we can store it in the form of MindIR, and the deployment on all the device include cloud and device or maybe the end edge. Okay, so that's all I would like to cover today. Thank you very much for listening. I'm not quite sure whether we still have time for 1 or 2 questions about my talk.
Yeah, maybe for one quick question.
Yeah, sure.
I guess the the natural question is, we're leading into the next talk, which is on JAX, I believe, or at least there's one later in the talk. What's the relationship sort of between like MindIR to the JAX IR?
Oh, so I'm not the expert for JAX, but I would like to maybe I talk a bit, and maybe the expert on JAX will correct me later. So in my understanding, MindSpore IR is like more like designed for the static graph. So we will not so we will represent the whole graph and compile it before running. I look a bit into JAX, so maybe the next speaker can correct me. So JAX, I think is more dynamic, and it has some tracing, and I think it's more dynamic graph friendly. And I think MindIR is more like static graph friendly because we have represent our whole graph during the compiling stage and before the executing stage. Yeah, so this is so I'm very confident about my comment on MindIR, but not very confident on my comment on JAX. So maybe next speaker can correct me. Yeah.
Right.
Thank you.
That's Zichun for the excellent talk again, and we can come back to the question later in the panel discussion session.
Sure.